All right, so remember tonight is the deadline for revisions on our second exam, right? So make sure you get those turned in or submitted if you want to. Okay, 11:59 p.m. Yesterday we spent time talking about a lot of new, well, really one type of reaction, but a lot of different examples of that reaction. Okay, so what we really looked at was the reaction of carbonyls, different carbonyl functional groups with hydride. Okay, so hydride is acting as a nucleophile. We saw two main reagents. I'm going to review this on another slide, but two main reagents to deliver hydride. One is very strong, lithium aluminum hydride, and the other one is weak, which is sodium borohydride. Okay? The net reaction of these reactions is reduction. Okay, so we're reducing the carbonyl groups. All right, so today what we're going to do is we are going to go beyond hydride, and we're going to look at some different carbon nucleophiles. Again, in this chapter, all of the reactions, though, involve strong nucleophiles. In the next chapter, we're going to start to mix it up and look at some weaker nucleophiles as well. Okay? Any questions? All right, let's do a clicker. Let's do reactions that we looked at yesterday. Okay, so these reactions, they're all involving the addition of hydride to a carbonyl. So they're all involving a reduction reaction. We're breaking them up or splitting them here by the strength of the reducing agent. Okay, so we have a strong reagent. Remember, that's lithium aluminum hydride, and it essentially reduces every kind of carbonyl. Okay, if that carbonyl has a leaving group on it, well, let's look at these groups. So these are what we called, I think, the type 1. They have a leaving group. Hydride displaces that leaving group to make an aldehyde, which is further reduced to a primary alcohol. Oh, except I extended that too far. We had one exception to that, and that includes the amides. So instead of losing that potential leaving group, which is nitrogen, nitrogen stays, but the oxygen gets lost. And so we form an amine. Okay, so a reduction with lithium aluminum hydride of an amide just gives the amine. We essentially remove that oxygen and add 2 H's there. If we have type 1, then the aldehyde goes to a primary alcohol. A ketone goes to a secondary alcohol. Yeah.
Which one's type 1? Are they both type 1s?
Oh, no. These are, I think I had, these are 2.
Oh,
Thanks. Yeah. All right. So the difference here is mostly whether there's a leaving group or not. If there's a leaving group, then it usually gets displaced to form an aldehyde, which is further reduced to the primary alcohol. Okay? If we use the weak reducing agent, sodium borohydride, it can only reduce aldehydes and ketones. All right? So it essentially does the same reaction on aldehydes and ketones that lithium aluminum hydride does. The difference here is, though, that sodium borohydride will not reduce carboxylic acids, esters, amides, these groups. Okay, so if we had more than one of those groups in a molecule, it's only going to reduce the ketone or aldehyde. Okay, and then we had two specialized reducing reagents. This was aluminum. This is tritert butoxy aluminum hydride. Its special job is to reduce acid chlorides to aldehydes, so it just reduces once, not the second time. And dibal, which is diisobutyl aluminum hydride, its special job is to reduce esters to aldehydes and stop after that one time. Okay? So those two are just very specific. So what if we wanted to reduce an ester to an aldehyde, but we didn't have dibal? We had other reagents, but we didn't have that. So let's say we wanted to go from here to here, and we're losing methoxy group or methanol on the way, but we have no dibal. Maybe we're in the lab and week before we finished it all and our new order isn't here yet and we just can't wait because our advisor is just like on our case wanting us to get it done right away. Huh? So is there a way using any of the reagents here with other reactions that we've learned before that we could accomplish this same transformation? Somebody outside the room was even going to suggest it. Nobody in here is, but somebody not even taking the class. All right, what else can we make an aldehyde from? Let's kind of go back this way. A primary alcohol is one other thing that we can make it from. Right? And how would we do that? What type of reagent? What reagent will do that? We usually use this PCC, pyridinium chlorochromate. Okay? How can we convert the ester to the primary alcohol? A reduction reaction, right? Look at the table up there. Lithium aluminum hydride. Okay? It's right here. So we can use lithium aluminum hydride followed by water, reduces the ester to the primary alcohol, and then we can oxidize it back to the aldehyde. Okay? So in fact, in real life, from my own experience, this dibal reduction does not always, on paper it looks great, it doesn't always work perfectly because sometimes you get a mixture of the aldehyde and alcohol. Okay? And so in those cases, sometimes it's just easier to reduce the ester all the way to the alcohol and then oxidize it back to the aldehyde, right? Sometimes two reactions that are very good are better than one that's not working so well. Okay, so sometimes there's other ways to do these or to combine these reactions as well. Okay? All right, so what we're going to do now is we're going to look at some carbon nucleophiles, some strong carbon nucleophiles that will also react with aldehyde. Well, not aldehydes only, but carbonyl groups. Okay? We're going to look at 4 types of nucleophiles. Okay, the first group, these are called, and I kind of, I think, introduced these before. These are the organolithiums. In each of these cases, we have a metal attached to the carbon in some polar bond, or at the bottom case, essentially ionic bond, that pushes electron density onto the carbon. Okay, because the metals are always more electropositive than the carbons. Okay, because remember, as we go down the periodic table, or we go to the left of the periodic table, it gets more electropositive. Okay, and so all of these make reagents that have a delta minus. Okay, so let's just look first how we make these reagents. Okay, so organolithiums we just make from the halide, the alkyl halide plus lithium, but we need 2 lithium. So these are lithium 0, lithium metal, okay, not the cation. And the byproduct from this is that we get 1 molecule of lithium halide, whatever the halide was that we started with on the. Okay, so we start with the alkyl halide. The next one, these are organomagnesium compounds. They had another name. We usually refer to them after the name of the inventor. Oops, Grignard. And again, in this case, we just start with the halide. And we add magnesium metal. Okay? In both of these cases, notice what we're doing is we're replacing a halide with a metal. So it's sometimes called metal halogen exchange. And both of these, well, let's talk about that in a minute. Okay, so that's how we make those 2. This is the organocuprate. Okay, and these we make from, the first step here is a organolithium, so we need 2 of these because there's 2 methyl groups on this organocuprate, and we react it with copper iodide. Okay, so of course the methyl lithium could come from something like methyl chloride plus 2 lithiums, right? Or basically in real life, if they are common organolithiums, you know, methyl lithium, ethyl lithium, butyl lithium is a common organolithium, you usually can buy them as a solution. Okay, and so it's in a standardized solution, whatever, 1.6 molar or something like that. It's in a solution, and the top of the jar has a septum on it, and you have to get it out using a syringe. Okay, because it's, as we'll talk about on the next slide, they're very reactive. All right, the last one we've seen before, this is an acetylide anion. And we can just do this one through an acid-base reaction because that terminal proton in an alkyne is more acidic than protons on sp3 hybridized carbons, which all the other ones were. So if we're going to make like that propyl lithium up there, if we just start with propane, the hydrogens, the protons are not acidic enough. We cannot just remove them by an acid-base reaction. We have to use this metal halogen exchange. Okay, so this we can do acid-base. We have to use a strong base. We usually use, oops, I did it right the first time. It's called sodamide, sodium amide. So it's NH2 minus, or we can also use sodium hydride. Okay, so all of these are strong nucleophiles, and they'll all react with at least certain carbonyls. Okay, the cuprates we're going to look for mostly at kind of specialized applications. All right, so if we have a very strong function as a very strong base, like I was just talking about for the organolithiums. All right, so these can also function as strong bases. So if we generate a Grignard or an organolithium, if we react that organometallic reagent with anything that has a acidic proton on it, all we get is acid-base chemistry. Okay, usually acid-base chemistry is faster than some nucleophilic attack. All right, so for example, if we reacted this 3-bromopentane with magnesium here, I'll draw the intermediates here, we would get this Grignard reagent, and if we add water into that, all right, it's not going to form, this is the common idea, but it's not going to add an OH on there, okay? It's just going to do acid-base chemistry, and our base is this carbon right here. Okay, so that carbon is going to react with water. This bond is going to go over here. It's going to go like this. And all we're going to get is pentane plus some magnesium salts or hydroxides and things like that. Usually some kind of mixture of things. All right? So if we have any water around when we try to do these reactions, all it does is acid-base chemistry, and we'll never get our nucleophilic addition reaction. Okay? So we have to do these reactions in the absence of all water. We usually do them in the absence of oxygen as well. Right? So we have to be very careful. All our glassware has to be usually oven dried. We usually put it under nitrogen. So an easy way to do that is if here's our round bottom flask, we put over the top here is a rubber septum. We stick it inside and then we flip it down over the sides, and so it seals it up, but it's rubber. And so then what we can do is an easy way is if this is a tube and we can stick a needle in here, this can supply some inert gas like nitrogen. Okay, so we flush out all the oxygen, any moist air that's around, and this keeps it under inert gas. And then if we add reagents in or out, we use syringes to do it. Okay? So our reagents never are open to the air. Okay? So if we have moisture, right, it just kills a reaction. All right, so if we do this again, we can start with something like chlorobenzene. We can make a Grignard out of that. But if we react it, or it's in the presence of something like methanol, methanol has an acidic proton, so the Grignard just reacts with the proton, does acid-base chemistry, and what would our product be from this reaction? What? Just benzene. Okay, let's draw this. The chlorine gets replaced by an H. So in fact, this could be a way to remove a halogen if you wanted to on a benzene ring, right? And down here at the bottom, likewise, if we make this organolithium, if we put that in the presence of a carboxylic acid, the carboxylic acid has an acidic proton, and all it will do is acid-base chemistry. So we would just get this methyl cyclohexane. Okay? So this is just something, we don't often do this on purpose, but it's a side reaction that we have to worry about. Well, or it could be on purpose on an exam just to kind of trick you, right? Or to make sure you know that. All right, so let's look at what we're really going for. Let's look at some nucleophilic reactions. All right, so let's start out by making these strong nucleophiles. So if we react this alkyl bromide with 2 lithiums, we make this propyl lithium. What if we mix that compound, or what if we add chloroethane to it? Yeah.
Sorry, on the last slide, what's acting as the base again? Is it the magnesium? On the last one.
All of the organometallic reagents, right? We're going to look at them now as strong nucleophiles, but they're all strong bases. Yeah. Right, and usually those properties go together, right? The strongest nucleophiles are usually the strongest bases. Okay, so we get this organolithium, and we treat it with another alkyl halide. What do you think would happen? Nucleophile with an alkyl halide. Have we ever seen anything like that before? Right? So what we would expect is a substitution, but in fact, it doesn't really work very well. So this is we're going to say no. It's not really no reaction, but what usually happens is the alkyl lithium that was formed through this metal halogen exchange can just react with the other chloride, and it can do other metal halogen exchanges, and so the halogens and the metals are just kind of exchanging, and they don't do what we want, right? So they don't do good SN2 substitutions. Same with the Grignards and alkyl halides do not do no SN2 substitution. Okay? So we can't use it for that. What about the next reaction down there? We treat this terminal alkyne with a strong base, and then we add chloroethane. What happens then? Will this do an SN2 substitution?
No.
Will it do a substitution? Yes, right? You guys learned this last semester, chapter 11, I think. This was the main way that you could use to extend a carbon chain. Right? Start with acetylene. You can deprotonate it, do an SN2 substitution to add an alkyl group. You can do it on the other end if you want. Right? So this is chemistry we can do. So the only way here that we really have a good way to do just straight SN2s is if we have an alkyne. We can't do it with just an alkyl group. Or an alkene, we can't really do it. All right? So another reaction that's very good is if we make this alkyl lithium, this strong nucleophile will do substitution reactions with epoxides. And I don't know if you guys covered this last time or not. I think it was in one of your chapters, but I had heard rumors that maybe at least one professor skipped this one. Okay, but basically what we have is we have delta plus on the lithium, delta minus on the carbon. So we have a strong carbon nucleophile, a strong basic carbon nucleophile. And so this bond is going to attack the epoxide at the less substituted side, and it's going to open up the epoxide ring. Okay, so we can get an intermediate. So there's our first three, goes to here, here. Did I write the same? Right, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And our O minus is going to go right here. So we've formed this bond. All right, we have the propyl group, attack the epoxide, open the ring, forms this alkoxide intermediate, and then we add water, and it just protonates the alkoxide, and we get an alcohol. So we've extended the chain, generated an alcohol. Okay. If we did the same reaction, but instead of using this 3-carbon epoxide, we just used the simple epoxide here, right? Then what we would get is just this primary alcohol. Okay, we're going to contrast this in a second with another reaction. So if we make a Grignard or a organolithium, we can do a reaction that adds 2 carbons and leaves us with a primary alcohol. It's a way to extend a chain, leaving us with another functional group that we can then do further chemistry on. Yeah?
If this original reaction was carried out in acidic conditions, would we get the substitution?
Right, so there's a question just about the epoxide reactivity, right? So when you learned about epoxide reactivity, and we had an unsymmetrically substituted epoxide like this, if we do it under basic conditions, so up to now it was more like hydroxide or methoxide or some basic conditions like that, it attacks at the less substituted side, okay? If we do it under acidic conditions, so you can do the same reaction, say with, instead of hydroxide, you can use water in the presence of an acid. And then the first step is to protonate the oxygen, and then the nucleophile comes in at the more substituted side, okay? All of these reagents we're looking at here are very basic, so they follow the basic pathway, okay? This chapter is about carbonyls, so let's finally get to the reactions of these strong nucleophiles with carbonyl groups. Okay? So we're just starting. I guess I really fell in love with bromopropane here, and so I'm using it over and over again. So again, here we're going to form the Grignard in this case. Essentially, when we draw these, right, we're starting with the halogen, and we just, the Grignard is just kind of inserting the magnesium between the carbon and the halogen. Okay? It's a way to remember it. Then, the way we draw a reaction is from the bond between the carbon and the magnesium. It's those electrons that are going to be the ones that react, because it's really functioning as an anion almost. So we have a very strong nucleophile. We have a simple aldehyde, formaldehyde there. What's going to happen if we react that strong nucleophile with formaldehyde? The reaction takes place. Where is it going to connect to the aldehyde? To the carbon, right? Because we have a nucleophile with a minus, and it reacts with the plus end of the carbonyl group, just like we saw with hydride. Okay, so this bond is going to go over here, react at the carbonyl carbon, and the pi bond, the electrons are going to go up onto the oxygen. Okay, so we're going to draw an intermediate here. Okay, let's draw our intermediate first. So there's our 3. We've added 1 carbon, and we now have O minus. Oops. And our 2 hydrogens. Okay, so here's the bond that we formed. And we added the 1 carbon and 1 oxygen. All right? We then quench the reaction by adding water. And this simply protonates this alkoxide. And we get a primary alcohol. Okay? So as opposed to the last reaction that I showed in the others in the last slide, in that case I took the Grignard, I reacted it with an epoxide. I added 2 carbons to give us a primary alcohol. Now I'm adding formaldehyde. It still gets us to a primary alcohol, but we've only added 1 carbon. Right? So we can add 1 or 2 at a time to get a primary alcohol. Okay? We can react Grignards with other aldehydes. So here's a little bit longer aldehyde. The Grignard would be formed from this bromobenzene. That would attack the aldehyde, and we would get this. After we protonate, we get this compound right here. Right? We've made this bond. So we start with an aldehyde, and in this case, we get, other than formaldehyde, we get a secondary alcohol as a product. All right? Could we get to that compound from benzene through a different series of reactions?
Just start with elimination, Br2 and iron trigonal.
Well, yeah, we could. So this one, if we wanted to start from benzene, we could start with just benzene like this, right? And then we just brominate that. Okay, but what about not going through that bromination, not going through bromobenzene? Yeah.
We could do a Friedel-Crafts isolation,
Yep. And then what?
and then we do a reduction.
A reduction.
Grouping and alcohol.
Yep, exactly right. We could do a Friedel-Crafts acylation, right, which would form the ketone at that position. And then, because we have a ketone now, we could reduce the ketone with a hydride reducing agent. You know, we could use sodium borohydride, or we could use lithium aluminum hydride, followed by protonating the product. Okay? So those would get to the same thing. So, and starting with benzene, whether we brominate it and then do a Grignard, or whether we do a Friedel-Crafts acylation followed by reduction, both of those are the same number of steps. Right? So we have some different ways to do these things. Okay? If we start with a ketone, I kind of switch this one around. Instead of starting with the halide, I'm starting with the actual carbonyl now. And we're just starting with this methyl magnesium bromide. Okay, so that can add to our ketone. The electrons go up on top. If we were drawing the mechanism here, we would get O minus here, and we added a methyl group. We add our water, protonate, and we get a tertiary alcohol. Okay, so Grignard reaction, or you could use the organolithium. If we start with a ketone, we get a tertiary alcohol. Okay? Just getting all kinds of cool reactions. Okay, so we can do these types of reactions with our type 1 carbonyls as well. Right? And it's going to, the difference between the type 2 that we just looked at and the type 1, presence or absence of leaving group, is going to have the same differences as when we were looking at the reactions with hydride. Okay, so when we use hydride, and if we reacted it with the acid chloride, remember the first step with hydride, displace the chloride, and we got an aldehyde. Aldehyde react again. Okay? In this case, we're going to use a methyl magnesium chloride, so a Grignard is going to react with the acid chloride. What's our first product going to be? Right, so this can come in, react with the carbonyl, just like what we saw on the last slide. Let's draw an intermediate here. Remember, once the nucleophile attacks the carbonyl, we generate a tetrahedral intermediate. Let's just draw these all out this time. Okay, we've added a methyl group. We have a chlorine still attached. Okay, what can happen at this point? Right, so is there a leaving group? Yeah, so there's a leaving group this time, and so these electrons can come down like this, and we can lose the chloride. Okay, it's exactly the same thing that happened when we used hydride, okay, when we were using lithium aluminum hydride. So what do we get from this step? What kind of a functional group? Ketone, right? What happens if we treat ketones with Grignard reagents? What do we get? We get, not secondary, right? From a ketone, we're going to get a tertiary alcohol, right? Because the ketone has 2 carbons on it already. We're adding another carbon, so we're going to have 3 carbons attached. Okay, so I'm not going to draw out the mechanism. This is the same as what we did on the last slide. We're just adding methyl groups. So we got, and after we protonate, we get a tertiary alcohol. So we can't stop this reaction after just one addition. Okay, the Grignards are too reactive. They're always going to react with the ketone. So usually what we'll have to do is add either double the amount, 2 equivalents of the Grignard, or an excess amount, and we'll just drive it all away as far as it can react. Okay? Same thing with esters. Okay? The Grignard adds once, kicks out methoxide, gives us a ketone, Grignard reacts again, and so it always also reacts 2 times. Like this. And we've lost in the process this methoxide, or after we protonated it, I guess it would be methanol. Okay, so those 2 are really reacting the same way. All right, what if we did a reaction of methyl magnesium chloride and we did the reaction with this lactone? Okay, so remember, a lactone is just a cyclic ester. So see if you can draw out what the product from this reaction would be. Yeah.
So is it appropriate just to write 2x for it if we're going to use 2 versions of it, or can we just do it all by itself?
Say again.
So you know I use 2 components?
Yeah.
So is that the correct way to write it if we were to do a synthesis, or can we just write the reagent by itself, since it's so reactive?
You mean without the 2 times or something? I guess let's go ahead and, to be consistent with everything else, to write 2 times or excess or something like that. Yeah. All right, so what are we going to get here? So we just have an ester, so it's going to react 2 times. It's going to cleave this bond right there, so we can draw it if we want after protonation. Let's just draw the carbon skeleton. We're not breaking the carbon skeleton. Right, we're going to get this alcohol here, and we've added 2 methyl groups at the position where the carbonyl is. Right? And so it can look even more confusing if we could just draw this like this. All right, so we have an ester add 2 methyl groups. This used to be the carbonyl. This is the alcohol portion of the ester, so it's been opened up. All right? It's always the same thing if it's in a ring. It just looks trickier. Okay? Other ones. Okay, the first one, we're just going to make a Grignard right here. But this time, instead of formaldehyde or an aldehyde or a ketone, we're going to react the Grignard with carbon dioxide. All right, so what do you think we're going to get out of this reaction? Okay, so we get our methyl magnesium bromide, and we're going to react that with carbon dioxide. So carbon dioxide is kind of like just a double carbonyl, right? So do the same thing that we did for all the other carbonyls, right? So this bond, attacks the carbonyl carbon, and some electrons have to go on to one of the oxygens. Doesn't matter which one. Okay. So what's that going to give us? So we're going to make this bond to the carbonyl. We have a double bond here, and we have an O minus. Okay. In this case, we're not using water. We're using some acid because we have a conjugate base to a stronger acid. Right? So we need to use a strong enough acid to protonate it. So what's going to be our functional group? Just a carboxylic acid, right? So we can add a carboxylic acid in one step. Okay, we form the Grignard, add CO2. This is an easy reaction to do. You just form the Grignard and you can just dump it in on some dry ice, okay, which is solid carbon dioxide. It's an easy way to even just test to see if your Grignard even formed or not. All right, so we'll finish this last one on Monday. All right? So have a good weekend.